go. Right. So anyway, what I'm going to actually do, because I put these notes in here just to have them, but I'm actually going to do number 2 over, right? And then we'll do numbers 3 and 4, because I just realized that, or thinking about it, it doesn't really make sense to just kind of talk about it without actually doing it. Because I mean, if I was going to do that, I'd tell you to just read it on your own, which doesn't help anyone, as you know. Right? If you could, honestly, if people could learn from or easily learn from written math notes without any kind of instruction, then there wouldn't be a need for actual instruction. All right, so let me kind of take this one from scratch, number 2, just going back to that, and just show you what the true solution ought to be. Right, it's very similar to what we were doing before or previously, but it's got that little extra twist to it. Right, so and it has everything to do with that denominator. All right, that denominator has a leading coefficient other than 1. Right, so what we're going to do is we're going to take that leading coefficient, or the leading coefficient of the numerator and the denominator, and make a ratio out of it. Right, so I'll show you. So there's an understood coefficient of 1 in front of the x squared. There's the coefficient of 3 in front of the x. We're going to make a ratio out of that. All right, and we call that the ratio of the leading coefficients. All right, kind of similar in idea to how you would go about finding a horizontal asymptote, if you remember from the last unit. If not, it's not a big deal. All right, but the ratio of those leading coefficients would be 1/3. All right, we're going to hold on to that ratio. All right, we're going to just kind of put it out of our mind for now and come back to it later. All right, now what we're going to do is take the coefficients of the numerator. Remember, x squared minus 4 is really the same as saying x squared plus 0x minus 4. All right, we strip it down to its coefficients. I mean, it is synthetic division, so that's not new. Then we're going to divide with the synthetic division process. All right. Now, just a little recap, the way we figure out the number on the outside, I mean, I took you through this whole approach of taking your denominator and setting it equal to x minus r. And that I mean, that led us down a rabbit hole that was pretty complicated. But whatever the result is, when you set the denominator equal to 0, that's going to be the number that you put on the outside. Right? So I would even say set denominator equal to 0 and solve. Right? That's what you would do if you were looking for a vertical asymptote anyway. So odds are you have to do that in some capacity. So 3x plus 1, set that equal to 0 and solve. I'm just going to smidge this down a little. All right, and when you do that, you get x is equal to negative 1/3. That number goes on the outside, and that's what we use in synthetic division. All right, so we're going to run through the synthetic division process. I mean, it's a fraction on the outside, so it ain't going to be pretty, but in terms of the ugliness, it actually, it won't be as bad as it could be because it's only 3 terms. All right, so we drag down that leading coefficient. We multiply by the number on the outside, which is negative 1/3. We add. We get a negative 1/3. We multiply by the value on the outside. We get a 1/9, but if you remember, that's going to end up being irrelevant because we're going to cancel out the remainder anyway. We're just going to drop it. All right, so whatever that product is, actually the part that makes this complicated in terms of the computation is actually going to disappear anyway. All right. So then this is where the twist comes into play. All right, what you need to do in order for this to work out the right way, and this is where I took you down kind of a road that I thought was the correct road, but it actually wasn't. And actually, and it's kind of interesting. I don't want to ruin the flow here, but I looked at different resources online, at YouTube, other websites and everything, and everybody's making the same mistake. Like everybody's doing it wrong. And I was shocked. Right. So what we thought, or I'm not even gonna insult you. What I thought last time was that x squared minus 4 over 3x plus 1 had an oblique asymptote of, remember, it was 1x to the first minus 1/3 x to the 0. Right. And so that's what we put in. And I was like, all right, in my mind, I was like, something feels wrong, but I followed the process and everything looks right. So I'm just going to go with it. And we moved on. Right. But that wasn't correct. Right. So what we need to do is multiply by the ratio of the leading coefficients. And you know what? I can't even stop myself. That's not what we do, because I even thought that was the right way, and it still isn't the right way. You multiply by some number so that the leading coefficient becomes the ratio of the leading coefficient. That's a mouthful. I'm going to write it down. Multiply by some number so that the leading coefficient of your OA, your oblique asymptote, becomes, in this case, the ratio of the leading coefficients that we figured out right in the beginning was 1/3. I want it to become 1/3. All right. So that number right here, I'll highlight it in green. I want that to become 1/3. Now, in most cases, and this is one way in which I easily confuse myself, is most of the time you're just multiplying by whatever the ratio of the leading coefficient is, but not always. There's some instances where it doesn't play out that way. That's why I created this extra example 4, which we'll go over in a couple minutes. All right. So what we're going to do is we're going to take that 1x minus 1/3, and we're going to multiply it by something, the result of which should give us a 1/3 x. All right. Now, as it turns out, that something happens to be 1/3. Right. It won't always be, though. When I multiply through with a 1/3, I get 1/3 x minus 1/9. And that's my oblique asymptote. So it's a minor adjustment at the end. All the other work had to happen, but it's a necessary minor adjustment. Right. So the 1/3 x minus 1/9 would actually be my oblique. And that actually looks more like an oblique asymptote, right? In the sense that the curve is actually approaching that blue line. Right. As it turns out, the vertical asymptote would have been the negative 1/3. So I could just pop that in there. X equals negative 1/3. But these would be the two asymptotes that define my rational function, right? The two boundaries, all right? Definitely something that looks more appropriate. I'll go over another one just, along these lines in a minute. So if you're not with it the first time around, I'll give you another example so that you can get the hang of it. But this is actually pretty important when it comes to this concept, the concept that we're going to talk about in future years. Not the least of which is right in the very beginning of Calc 1. So, it is necessary. So it's not like hey, I discovered something fun, let's talk about it. It's more like, I'm shocked that I myself didn't know this particular condition related to oblique asymptotes for all this time. And, you know, it is what it is.
Yes, sir. I don't understand at all why we had to multiply by some number. Like what did you see that we didn't see?
What happens
All
is
the
when
other
you're dealing,
stuff that you were showing us, like we you know, number one and everything else before this was easy. Like how did this example stick out so that you had to go research things you didn't even know?
so when I created the graph, that oblique asymptote, it looked like this. All right. And at first glance, it was like, all right, fine. It looks like a line. We wanted a slanted line. We got a slanted line. Perfect. The problem was an oblique asymptote has to be a line, a slanted line that the graph actually approaches as you move outward from center. So when I looked at later on after the fact, I was like, wait a minute, not only is this red curve not approaching that blue dashed line, it's actually getting further and further away from it as you go out. Right. So it's actually doing the opposite of getting closer and closer to it. Right. So that was a red flag. I was like, there's got to be something wrong here. There's something I'm missing. Right. So when I spent a fair amount of time investigating different multipliers and different ways to figure it out. And basically what it comes down to is whatever the slope is of the rational function, as in the ratio of the leading coefficients that registers as the slope of the rational function, that has to be the slope of the line, right? In order for, and you see here, after I make the correction, the curve does approach, you know, it's at some distance away from the blue dashed line here. But as I increase my X value, you see it's getting closer and closer together, right? And that's what an asymptote should do. With the correct asymptote, it looks appropriate. With the incorrect one, it looks anything but, you know, but without having a sense, I mean, honestly, could have just moved on to the next topic, never said anything. You all go off into Calc 1, get all these questions wrong that you could have been getting right, and it'd be all my fault. And honestly, I feel bad. I got years of students that I didn't teach completely. I mean, there's some aspects of this that were correct, but there were some like this, there's one condition that might be a big deal that I totally failed them on, and I feel terrible about it. Right? So now it doesn't really come up very often because you see here, the leading coefficients are 1. So the ratio of the leading coefficients, I'll use LC to represent leading coefficients. The ratio of the leading coefficients, 1/1. And so it's very easy to lose sight of this relationship because in a lot of cases, the multiplier is a 1, so it doesn't even matter, right? But if you go through this process, you know, you drag out the coefficients. We have x squared plus x minus 6. You get a 1, a -6. This one's a little simpler. We don't have to go too crazy. The x minus r gives you a -1. So r is equal to -1. All right. So that's one of the more basic situations. When the leading coefficient is 1, it's not too bad. Bring down the coefficient. You get a 1, multiply by the outside, you get a -1. Add, you get a 0 in this case. Multiply, you get a 0 again. Add, and you get something that we don't care about because we're going to drop it anyway. All right. So now I have a 1 and a 0, which if I put my x values in, x to the first, x to the 0th, we would check and see if that actually gives us the appropriate oblique asymptote. But we need to multiply by some number so that the leading coefficient of your oblique asymptote becomes whatever the ratio that we determined earlier was. Well, in this case, the leading coefficient already is that, right? Whatever this number is, this number needs to be the same. All right, so these two, and I'll use a red highlighter, reddish highlighter. All right, so we have this number here, and this number here have to be the same. If they're the same, then you're good, and we have identified our oblique asymptote. So y equals, I mean, this is going to cancel out, so just y equals x. But you take a quick look graphically, we have x squared plus x minus 6, and then the x plus 1. And then, let's see, my oblique asymptote is just y equals x. Get rid of that, we don't really need it. And visually, it does appear that as we go out in terms of x, that our curve, our red curve, is getting closer and closer to the blue dashed line. All right, so it actually gets very close to it very quickly. So you're like, what do you mean it gets closer? It's already there. Well, if you zoom in, you can see that there's still space, and that space is closing as you keep scrolling along. It's very, very slow in terms of how that rate of change is changing, I suppose, the distance between the red and the dashed line. But you can see it's not quite at the same location, and we're already at, into the 100 range, right? But that would be our oblique asymptote, and it satisfies the definition. All right, so one more, just to kind of drive this point home. Again, we find the ratio of the leading coefficients. All right, so that is a 3 and a 7. So in this case, 3/7. I'm going to hang on to that number. All right, I'm going to take my denominator, because the denominator is not a simple one this time. Over here, it was not bad. It was just x plus 1. Now I'm looking at 7x plus 6. That's pretty ugly, right? So 7x plus 6, I'm going to set that equal to 0 and solve. All right, so that's simple algebra, nothing too fancy. All right. So this is our R value. This is going to go on the outside of synthetic. All right. We're looking at 3x squared plus 6x plus 1. I'm going to type that in. 3x squared plus 6x plus 1. And on the bottom, I'll put my 7x plus 6. I'll get rid of this asymptote here. So this is what we're up against. So whatever we plot as an oblique better kind of jive with those two diagonal parts of the curve. All right, so I'm going to grab my coefficients 3, 6, and 1. I'm going to make my little diagram here with the negative 6/7 on the outside. That's exciting. And I'm going to pull down the 3. All right, 3 times negative 6/7. Geez. All right, so negative 18/7. All right, I got to add that to 6, and you're like, oh, this is getting crazy. But really, I mean, 6 minus 18/7. That's not too bad. I mean, you see this hideous decimal, but that little fraction icon next to it, if you tap on that, it'll convert it over to a fraction form for us. So that's not bad. Then we would multiply that by negative 6/7, get a number here. But then we would add that to the 1, getting a remainder, but then we're going to drop that anyway. So who cares about what this number is? It's irrelevant, right? So what we need to do at this point is guarantee or make an adjustment in such a way. Oh, that's not what I want. We want to make this coefficient the same as whatever the ratio of the leading coefficients is. All right. So that 3 needs to become a 3/7. All right. So we just kind of reflect back to what we have here, thinking about, all right, well, this is going to be a linear equation. We'll bring it in a little bit. So this is an x to the first and x to the 0th. We get a plus sign here. All right. So this would really be, if you kind of bring it down, we'd have 3x plus 24 over 7. All right. Now, if I incorrectly assumed that that was my oblique asymptote, which I would have done as recently as a couple of days ago, that red curve, the slanty one, as it's going to the right, it's getting nowhere near that black one, so it can't be right, right? So this 3 needs to become a 3 over 7. The way we do that, I want a 3 to become a 3 over 7, multiply by 1/7. Okay, and so we would get, as a result, 3 over 7 x plus 24 over 49. And that would be our oblique asymptote. It's hideous, but it would be correct. So 3 over 7 x plus 24 over 49. That actually looks like a line that the red curve is approaching. So that little correction is what gets the job done, right? And so just tack on a y equals and you have your oblique. And just kind of throw it in front. So this is our OA. All right, so it's that little adjustment at the end that makes all the difference. It's kind of crazy, but it makes a big deal. Wouldn't it be 16 minus 18? Or when do you do? It's going to be a positive 6 when you do the addition, because we're just pulling that 6. This 6 comes right from this equation here, or well, in this case, an expression. So we bring the sign along with it. So we're taking a positive 6, adding to it negative 18 over 7, which is the same as 6 minus 18 over 7. So that's the concept of an oblique. Quick review on that. And then now we get to the removable discontinuities. And that one was a little bit more tech heavy. Although you might look at this and say, well, it was very tech heavy, but there's a lot of algebra going on, a lot of computation. All right. In the case of number 3 on the next page, remember the process: factor numerator and denominator. I apologize, I have my window open and people are very loud outside. If you could even hear it. Factor numerator and denominator, cancel any like factors, graph the original function and simplified function. Look for where the original has undefined value, but the simplified function doesn't. Right? I'll say it's as simple as that, but what I mean by that is it's not always going to be easy. It's just a matter of, it's a straightforward process, follow the steps to get the answer. Right? There's no hidden steps like with the oblique asymptote. Right? So factor. X minus 2, x minus 3 are the factors of x squared minus 5x plus 6. All right. Now we look for a common factor, and we actually have a common factor. It doesn't seem that way right away, though. So h of x is equal to, so x minus 2, x minus 3, but the numerator, it doesn't look quite exactly the same as what we have on the bottom, but it's actually the exact opposite. If you factor out a -1, you would get the opposite of what we have here, which would be x minus 2. All right. So -1 times x minus 2, and now we have a common factor. Okay. And if you don't like that, that's fine. A lot of people just memorize a rule. And that rule, I'll just kind of jot it off on the side. This is like from old school algebra. And that is a minus b divided by b minus a is equal to -1. And the bottom line is that you're looking at two things that are exact opposites of one another. Right? Any expression that takes that form would have a result of -1. Right? So either way, but what we end up with as a result after the cancellation is a new equation, 1 over x minus 3. All right. So when we put that into Desmos, we want to do it as two separate functions. So h of x, you can use whatever you want of x. I called it h of x just to kind of mix it up. But you can go back to f of x if you want. Doesn't make a difference. You just want to be able to distinguish one function from another in Desmos. So h of x is the given function. I want my simplified function to be something else of x, assuming I want to evaluate. Right? You could call it y also, y equals. It's really up to you. I just tend to want to make it some other kind of function. So maybe like, g of x. All right, but you could, like I said, you could use y equals also. All right, you just turn one off, turn it back on, make sure they map to the same location. And again, I like to make, I mean, you've seen me do this enough. I like to make one dashed, so it's a little bit more obvious. And it's just personal preference. And so then what I would do here is make a table out of the two functions. All right, you see those two little table icons. I have my two functions, the original and I got the extra crispy. So I make a table out of each one of them. So my h of x has an undefined at 2. And I'll make a table out of the g of x. And you see my g of x, I mean, I know it kind of jumps all over the place here on you, but if you scroll back and forth, you can see h of x has undefined at 2. G of x is not undefined at 2. Right? So h of x is undefined when x is equal to 2. I called it y on paper, so I'll call it y here. Y is undefined. Well, actually, it's not. I don't know why I went into a little groove there. Y is not undefined when x is equal to 2. All right. One of them's undefined, the other isn't. All right. So what that tells me is that there is a hole.
Professor, could we just go over really quickly in Desmos how you got the graph? You kind of went fast with that. Like how you got this. Yeah.
So you tap on the little gear icon.
Okay, tap on the gear. Hold on, let me just write that down. Sorry. Go ahead.
Then tap on the little table looking icon.
Okay.
And it'll make
And
a
it
table.
does it for you?
Yep. And you do it for each function. So gear, go down to G now, tap on the table, and you
Thank
have
you.
it. No problem. So we know that there's a hole at x equals 2. We just got to figure out the coordinates of the hole. All right. So what we would do is, well, I personally like to look at the original function at that location. I just turn everything off except for that original function at the x value of 2. So I just kind of scroll along and I see undefined at the x value of 2. And if you can eyeball where the y value is at that location, then you have your answer. The y value is at a result of 1, if I can get it to stop moving on me. But the thing is, you run into a little bit of a problem here sometimes when it's not quite so clean. In this case, very clean. Right? So that's where the table approach comes into play, because I can see here clearly undefined at 2. but that corresponds to a closed circle in this table of values for g of x, 2, 1. So on this graph, where they say a hole, the blue curve actually says that there's a point at that same location having a coordinate value of 2, 1. So that hole is at the coordinates 2, 1. Now, it does beg the question, what do you do if it's not a clean value that the table just flat out gives you? I mean, the values that we've got for these three examples were kind of served up on a silver platter, right? They're all either 2 or -2. They're tailor-made for a table of values, right? But what happens if it's not nice and clean, right? So if you need to investigate, and I'm just gonna do what I did before, I'm just gonna get rid of this graph here. All right, so if the x value of the whole is not easily found from the table, set your common factor equal to 0 and solve. That'll give you the x value of the whole. All right. Even if it's hideously ugly, it'll still give you the x value of the whole. All right. So my common factor was an x minus 2, but the common factor was the thing that was canceled out. All right. So that would be this. So x minus 2, set that equal to 0 and solve, you get x equals 2, and then that would give you the location of the hole. This is what I want. I was putting my arrow to the wrong thing. All right. So you could get it algebraically also. And that allows for instances in which it's like a hideous fraction. So, you know, I can just kind of make up an example here real quick. So I'll make this example for there was 3 examples right here. So we'll call this 4. And we'll say we have f of x is equal to 3x minus 7 over, now I gotta think. So 3x squared negative 4x minus 7. Geez, I hope that works. And we'll find out in a minute. So let's say you have this example here. There should be a common factor of 3x minus 7, right? You factor everything. So 3x minus 7 is one of the common factors. The other one, well, my intent was to make it x plus 1. So we'll find out if that's going to work. Outer 3, inner. Yeah, I think it works. All right. It's the danger when I make a problem up off the top of my head. All right. So we're looking at these being the factors. And so that common factor of 3x minus 7 would cancel out. And so we'd get a simplified function of 1 over x plus 1. All right. So let me show you what that would what would happen with that on Desmos. If I type in f of x is equal to fraction 3x minus 7 and 3x squared minus 4x minus 7. So we get this graph, right? Then I could type in my y equals 1 over x plus 1. Same graph. So we're in good shape here. You can verify. Looks pretty good. But then you go into the table. Little table action here. I got an undefined at -1. For this one, I also have an undefined. I'm sorry, undefined at -2. Well, actually, no. What is going on? Yeah, no. In both cases, I have an undefined at -1. I'm just looking at the wrong thing, right? So undefined at -1, undefined at -1. That's not a hole. That's a vertical asymptote. You can see it right here. I mean, I could just I'll type it in, x equals -1. I mean, if you have any sense of what the definition is of a vertical asymptote, then you recognize that instantaneously. All right, so we're good to go there. The problem is we should have an instance, if there is a hole in this graph, we should have an instance where it's undefined for the original function, but not undefined for the simplified function. Right? That doesn't mean, just because you don't see it in the table, that doesn't mean it's not there. So what we would have to do is take our common factor, set it equal to 0, and solve. All right, so 3x minus 7, set it equal to 0, and solve, add 7, 3x is equal to 7, divide by the 3, and you get x equals 7/3. All right. What this is saying is that there's a hole at the x value, and maybe you didn't see this comment, I wouldn't have. There's a hole at the x value of 7/3, right? All because there's a common factor, right? So what I do is I expand my table. I type in 7/3. It says undefined, all right? So we're good. That means that there's a discontinuity there. There's a hole in the graph. Right? I'll type it into my simplified function, also 7/3. Now it says 0.3. Right? So for the original, there was an undefined at 7/3. For my simplified, that gave me 0.3 as a result. So the hole is at the coordinates 7/3, comma 0.3. All right. Definitely a little on the interesting side, but yeah, I just wanted to go over that one weird case, because every now and then you come across something that's it doesn't quite fit the mold of the quote unquote easy situations, and I hate to be the person that does all the easy ones in class, and then on a test I'm like, all right, here's one that you haven't seen before. I don't want to do that to you. So I figured I'd throw this in here. Right. So let me stop this recording, and